All right, so very happy to see everyone in my YouTube channel again. So we have an update for quite a while because I just started a research group at FSU. There are a lot of things to do in the past 2 years. So now I'm returning, so I'm gonna give more research updates and research presentations, and also hopefully some quiz about computational chemistry related stuff and computational material science related stuff. So today I would like to share a little bit about my ACS talk at 2024 in Denver, which has happened actually last month. It's kind of a summary of what we have done in disordered battery materials. So the title is Harness Extreme Disorder for Data-Driven Design of Novel Battery Materials. Okay, so and the story started with a schematic saying that this is how typically people are gonna imagine disorder, right? So this is when like a carrier moving through a well-defined energy landscape. Typically, we have some kind of a well-defined activation barrier which dictate our diffusion mechanism. And when you have disordering in the lattices, things will be a little bit different, simply because when the carrier moves through the energy landscape, the local environment will be very different everywhere, so that you're gonna have very different diffusion barrier, right? So it's kind of a bumpy energy landscape. So in this presentation, I'm gonna give three are examples of what exactly are the difference for disordered energy landscape, and how do we control and manipulate disordered energy landscape. Okay, so the first story is actually some of the old story if you keep watching my videos, right? So it's pretty much related with disordered rock salt cathode. The story starts when we started, manganese zirconium oxide and manganese titanium oxide. We see that these two materials will have very different voltage curve, even though that they have the same amount of lithium, they have same amount of manganese redox. But if you make them into battery, capacities actually differs quite a bit with each other. So this is not because they have the same crystal structure, but instead because they have very different short range order structures, which can be reflected by these diffusive scattering features as shown in the selected area electron diffraction. Okay, so this short range order is defined as the Pell probability. We typically use Warren-Collie short range order parameters. When this parameter becomes zero, it's fully random. Otherwise, we have chemical short range order going on. So a Fourier transformation of it will be actually the diffusive scattering intensities, right, by definition. So naturally, this is actually connected with diffusion, because I also want to remind you about this old literature that the short range order gonna changes how the important local structure 0 TM units arranges in the DRX structures, right? So, and from DFT calculations, this local structure have low enough diffusion barrier, so short range order eventually gonna change, the percolation network formed by this 0 TM channel. So what exactly gonna happen, right? So we're gonna have different short range orders, and those short range orders hopefully gonna change percolation network differently. But the problem is like how exactly that can work. So we would like to present our very recent publications, right? So what we see is like short range order features pretty much can be categorized into three types of conservation of bulk compositions in local units. So it's pretty much conserve the bulk compositions in tetrahedral local structures, octahedral local structures, and the cubic local structures. And then when you take a Fourier transformation of them, you can actually derive what will be the 2D diffraction pattern. And then we realize, all the short range order features that we see in DRX is pretty much a convolution of three basic structures of basic short range orders, right? So the first figure is like a combination between the octahedron type of short range order with a cubic type. Okay, so if you go from the top to the bottom, Okay, so the diffuse scattering feature is gonna evolve from a ring to some kind of a square. Okay, so that's essentially when you mix the octahedral type with the cube type, which is the second row and third row on the left hand side. On the other hand, and also this can be mapped into experimental observations. We see a ring for a lot of manganese, manganese-based oxide, and if you have oxyfluoride, the diffusive scattering feature will more look like a square. In addition to that, we also see that if you mix octahedron with tetrahedron type of short-range order features, you're also going to have different involvement of diffusive scattering features, starting from the ring and end up with a 4-point local contrast maximum. Well, the first one is the same compound with manganese-based oxide. Well, in the middle, you're going to see this kind of, four local contrast maximum, as some of the example will be manganese zirconium oxide. Okay, so in that case, we actually did a bunch of more samples, and eventually we can map everything back into a linear combination of 2 or 3 of these basic short-range order features. In addition to that, we can link that into the long-range order structure, right? So think about that. The tetrahedron local composition conservation is essentially analog to a long-range order structure, which is gamma lithium oxide, because in this kind of a structure, all the tetrahedral local environment have 2 metals and 2 lithium. Okay, so this is essentially a fingerprint of electrochemically inactive material called gamma lithium oxide. In addition to that, the octahedron type of short-range order feature actually exists in all typical ordered phase, including the layered spinel gamma lithium oxide. They all have this local ordering, so it's kind of a neutral short-range order features. And the cube type of local structure is actually something special. There's no long-range order structures for metal oxide, but we do see that in some intermetallics like silver zirconium, we actually have this unconventional layered ordering going on, because the layered ordering is actually across the 110 direction instead of the 111 direction in typical, for instance, like O3 lithium carboxide. And then if you analyze the percolation, you're going to realize, the tetrahedron percolation is terrible, and octahedral percolation is kind of in the middle, because all the order structure have that local unit, and the cubic short-range order is slightly better compared with the tetrahedron and octahedron type of short-range order. Okay, so that's so far our understanding a little bit more about what are the short-range orders available in DRX and how that gonna changes lithium percolation. In order to model that, right? So our group is actually constantly working on developing, class expansion tools. Okay, so and nowadays we can reproduce what we see in experiments from simulation at exact, synthesis conditions with class expansion based Monte Carlo, and also we can extend that capability into the modeling of neutron PDF. So this is just one example, right? So which we present before in other videos, that our model will be able to model to simulate exact amount of percolating lithium as a function of compositions, right? So we did 6 composition experiments. Well, our computational simulation can well reproduce what people see in experiments. In addition to that, we are ready for our end of the first story, right? So what is the difference for disordered energy landscape? Okay, so the major difference is like in a disordered energy landscape, you have to ensure a percolation of some kind of optimum local structures, right? So naturally, we're gonna have a question, right? So what if, the optimum local structure can never be exist or has never been found in all the non-materials? Can we introduce a local structure that did not exist? Okay, so this actually comes to our second story. Okay, so because we sort of realize, diffusivity of DRX is actually not that good. Okay, so it's okay as a cathode, but not so good as electrolyte materials. Particularly from GITT measurement, we see that the diffusivity is pretty much in the ballpark of 10 to the power of negative 13 centimeter square per second. For super ionic conductor, we're looking for something larger than 10 to the power of negative 10 or 10 to the power of negative 9 centimeter square per second. So naturally, there's still a difference between a good cathode, a high-rate cathode materials with a good electrolyte material. So naturally, we need something new, right? So here we present a funky local structure, which I propose that maybe we should add a little bit more lithium into the disordered rock salt so that you have actually cation ratio larger than 1. Okay, so because of that, I call it funky because in that case, 1 tetrahedron lithium will phase shell with 4 octahedron lithium. Okay, in that case, you don't have a very squeezed local structure which may not be so stable. So in that case, you may or may not be able to synthesize this compound. Regardless of the synthesizability, one thing we can test ahead of time is to do a high super screening across, these redox inactive metals. Okay, so we screen a bunch of redox inactive metals or typical metals as solid state electrolyte, and we sort of see that there has been some kind of optimum radius which will stabilize those specific metals in the overly aided compound. Okay, typically you have to have a large enough ionic radius. Okay, so something like scandium, indium, and yttrium will be better in terms of stabilize those overly aided disordered rock salts. Okay, so some of the good news, right? So here the dark blue tells you that the energy bell is kind of around 60 MeV per atom. This is pretty much the same energy bell as one of the well-known material, lithium manganese titanium oxide. So it's possible that we can make them experiment. And then we go to experimentation, and we do see that, if you heat up precursors, indium precursors, tin precursor, and lithium precursor, and mix them together, doing those typical solid-state reaction, if your annealing time is optimum, you're gonna end up with some interesting phases that is ionically conductive. Okay, so starting with 4-hour samples, typically you're gonna form DRX immediately, but you're gonna have a new phase called the S phase and lithium-3 NiMo3 phase. And if you keep anneal this sample a little bit more, you're gonna get rid of the impurity of lithium-3 NiMo3, and eventually you got a true phase made from DRX and S phase. If you keep heating these materials, lithium loss is gonna happen eventually. You're gonna lose a lot of lithium and you're gonna evolve into something totally irrelevant. But if you stop the reaction right away at 7 hours, we're gonna end up with a two-phase composite that has about 0.3 millisiemens per centimeter of ionic conductivity. Okay, so the S phase here, which is a new phase, right? So this is a phase that looks like DRX, but it prefers phase sharing tetrahedron lithium with only octahedron lithium. This is like a specially ordered type of DRX. So let's just zoom in a little bit to see the comparison of these two DRX structures, right? So the first one is the typical DRX structures. You're gonna have all the cations randomly distributed in the in the octahedron site, and in the tetrahedron site, ideally we also have a random distribution, but it also makes sense. They are mostly lithium. Okay, so in the S phase, S actually stands for spinel. This is not a real spinel because we do not have the right stoichiometry, but the cation ordering pretty much follows actually the spinels. Okay, so we have kind of a 16C and 16D octahedron ordering going on for the spinel, while at the same time we actually have tetrahedron lithium only stay in the 8A site. So this is more like spinel-like a disordered rock salt type phase. Okay, so a mixture of these two phases actually make the ionic conductivity even better because the S phase have a local a locally lithium-rich environment, because 8A site only phase gel with 16C site. That means all your lithium gonna diffuse through those connecting network between 8A site and 16C site. Okay, so we simulated the ionic diffusivities of both phases, and we do see the confirmation that S phase have even higher ionic conductivity compared with DRX. DRX has conductivity of like 0.1. S phase is pretty much like 3 to 4 millisiemens per centimeter. In addition to that, we did experiment and verified, we have similar conductivity. It's kind of in between DRX and S phase because we have a composite, or we have a diffusion barrier of like 250 MeV. Okay, so and we also kind of simulated the local hopping barrier, which also agrees well with the NMR measurement. All right, so now we finish the second story, right? So disordered energy materials, even if you do not have the local structures, what you can do is like sometimes you can artificially introduce some local structures and make them percolate. Okay, so naturally the last question is like, do we have a universal theory about it? Right, so the answer is yes, but in the very beginning I kind of struggle a little bit about it, because if you look at the energy landscape of disordered materials, you're gonna frequently see this kind of a localized trapping state, right? This is actually a bad thing, right? So because you're gonna kill the the carrier concentrations, because a lot of carriers gonna be trapped in those local energy minimum. Okay, so the disorder can actually kill carrier concentration. However, if there is a low enough barrier diffusion channels that can percolate, diffusion is not actually an average property. So if you have like half of the carriers trapped in some local minimum, it's actually not a bad thing. It's not necessarily a bad thing as long as you can trade off with low energy diffusion barrier. In that case, you can still end up with high ionic conductivity, especially the barrier goes exponentially with ionic conductivity. Okay, so this actually drives us to think about if there's any general rules of promoting ionic conductivity, right? So we pick up one of our favorite material, nasicon, which is also widely studied as superionic conductors and battery electrodes. So in these materials, we have 6B side and 18E side with well-dictated side energy differences. Well, in that case, if you introduce some sort of a disorder, in order to do control experiments, we fix all the chemical species, but we only introduce a random bond distortion, because when you mix different cations with each other, the first consequence is that you're going to have bond distortion, right? So the bond length will be different locally. So we introduce a bond length distortion of about 0.1 angstrom. And we do see that, in the very beginning, there is a very large side energy differences in sodium zirconium phosphate, which make it a terrible conductor. But once you introduce a distortion, you can effectively overlap the side energies between the 6B side and 18E side together. Okay, so in that case, there's a chance statistically that you're going to have very close side energies, and things will start to diffuse with low barrier. We did a percolation analysis on that, and we do see that, when you have enough side energy differences, the undistorted structure have to percolate at 850 MeV intrinsic barrier, right? So, but with distortion, 22% of the sodium can start to percolate as with the intrinsic barrier of 140 MeV. And if you can allow side energy differences a little bit more, you can actually percolate about 50% of the sodium. Okay, so this kind of ring the bell, distortion actually percolates at much lower threshold if you introduce them in the right way. Okay, and we didn't realize this effect is actually generic. Okay, so we did the same calculation for lithium nasicon. We did the same calculation for lithium garnet. For both cases, we do see that a certain fraction of lithium start to percolate with low enough diffusion barrier, which means the ionic conductivity can be good enough for those materials after introducing the lattice distortion, and also the fact that they have very different structures also rings the bell that this is probably like a generic effect. As long as we create a side energy overlap, it always promotes side percolation. Okay, so we did experimental confirmations as well, and the way we introduce large enough and random enough of bond length deviations to throw cooperating multiple cation species, right? So we synthesize some high entropy nacicons for lithium and sodium version, as well as high entropy garnet. For all the cases, we do see that the ionic conductivity increase by orders of magnitude with respect to the low entropy counterpart. So that kind of rings the bell. High entropy is actually a way to further tune the ionic conductivity of superionic conductors. Alright, so now we finished the last story, and I hope I convinced you, what we have learned from disordered energy landscape for disordered materials, and also reviews exciting facts, also some exciting opportunities. We've actually published this comment very recently, saying that high entropy materials is kind of overlooked. It have a lot of promises and potentials in the field of batteries, and also in many other field of clean energy and energy storage and conversion. Okay, so we sort of realize the short range order can be compressed if you have more cations, and gonna frustrate the energy landscape. Sometimes also gonna reduce volume change, and you can hopefully replace critical metals in the cathode counterpart of materials. Like we can get rid of cobalt and nickel, or at least minimize them. Okay, so being inspired by this kind of promises, what we do next is actually we're building databases, and we are trying to understand if we can use big data to explore high entropy materials. So recently we published a paper in Chemical Archive right now, and we kind of benchmark our data set with different kind of a graph neural network. Okay, so we have a local high entropy DRX data set, which have about 20,000 of high entropy DRX DFT data. And we do see that we can have a very reasonable amount of mean absolute errors by feeding neural network models into those high entropy DRX data. Okay, so which 2.4 MeV per atom is quite close to is much slower than the entropy you can actually introduce, or also the extra free energy you can introduce by mixing different cations. So hopefully our model will deliver very reasonable estimation of these orderings. In addition to that, we do see that there's a risk of using machine learning blindly, because when we model these high entropy materials, there are typically two ways of doing that, whether we use electrostatic ground state, or we use special quasi-random structures. Okay, so we do see that if you just use the special quasi-random structures to train the model, the prediction of the electrostatic ground state will be horrible. I mean, this 29 MeV per atom of error is pretty much close to a dummy model that assumes average energy to predict any possible compositions. Okay, so that means even though you have like 10,000 of DFT data with SQS, this model trend can be totally useless. In addition to that, we also see that unsupervised learning like PCA, they cannot really figure out the difference between the electrostatic ground state with SQS. Okay, so all we need to do is actually to understand a little bit better about the physical intuitions of those structures, because they intrinsically gonna have very different relative energies. In addition to that, we are currently building a database called HelenMD. It's a specialized database on high entropy energy materials, and we are trying to establish this database and fulfill data into these databases. And I hope these databases will be openly available in the next few years. Okay, so that's pretty much about my presentation. I'd like to thank my current group, and also a bunch of computing resources, and also our sponsors for the high entropy battery materials. Okay, so that's pretty much for my presentation this time. I will see you guys next time.